Artifact. It's actually old dog, new tricks, forensics with PowerShell, but this is a different slide deck because I just transferred them at the last second. Very similar. I work for VeriScript's Adaptive Threat Division. What I do there is I'm the Hunt capability lead for the Adaptive Threat Division. Hunt, kind of the idea there is if you're a large enough organization, there's likely somebody that has the motive and the means to get access to your network and do malicious things. And so hunting is kind of that concept of making your security posture or kind of using, preempting your security posture in the sense that you're operating under the assumption that there is somebody in your network and you need to go looking for them. I am the 2015 Black Hat Minesweeper Champion, so I'm really good at Minesweeper. Literally the proudest thing in my life is winning the Black Hat Minesweeper Championship. I'm the moderator at PowerShell.com security forum, so if you have any security questions, feel free to stop by there and ask them, and we'll get you an answer. I developed PowerForensics, Uproot IDS, and WMI Venti, which I'll talk about all of those sometime throughout this conference. And then I research forensic artifacts, which I'll get into. My background is that I started working in forensics with the US Air Force for about 5 years or so before I came to VeriScript. So in general, what is PowerForensics? Well, PowerForensics is a PowerShell module for live forensic investigation. Specifically, disk forensics is what we'll be talking about. It's a binary module, so it's a compiled C# DLL. Chose to use C# for efficiency and speed and a couple other things. Classes, for example, as Bruce was talking about in the last session, classes are available in PowerShell 5, but up until then they weren't something you could leverage. And so being able to have classes in that object structure was very important for me. And then currently it parses NTFS, the new technology file system, and many of the Windows-specific data structures, so such as the Windows registry, the Windows event log, scheduled jobs, and prefetch, and I'll kind of go into that. When I first started designing PowerForensics, and sorry I'm going a little faster through these slides, I'm going to try to catch up on time, I specifically was looking to parse raw disk structures and be forensically sound. So in general, if there's a bad guy or you're assuming that there's an attacker on a system, you don't necessarily want to use the Windows API because there's tons of ways that an attacker can give you false data from the Windows API and all kinds of stuff. So we want to be forensically sound, not trust the operating system, but trust our own code to parse NTFS. We also don't want to kind of muck up forensic evidence, and so things like timestamps on files and things of that nature, we don't want to alter those, and so I'll talk about how we get around that. We want it to be able to execute on a live or running host. We want it to be operationally fast, so traditionally forensics as a field is a very slow process. You would make like a full disk image of a terabyte disk, and then you would spend 2 or 3 weeks investigating that disk image to determine what happened on the system. Well, in the assumed breach mentality in an enterprise network of 100,000 endpoints, you don't have time to spend weeks on a system to determine what happened. You need to be able to spend minutes or seconds on a system to try to figure out whether or not there was truly something malicious going on. Also, I want to really focus on modular capabilities, and so basically you form these building blocks, and it's kind of that monadology, to where you form a building block, and then the next commandlet in the chain is going to build on that building block. So for those of you that are familiar with like DD, the DD utility in Unix, I have invoke forensic DD, and so that just reads raw bytes from a hard drive. But then I'm able to leverage that capability in parsing the master boot record, for example. And then it's capable of working remotely, which at this stage there's some proof of concept code, which hopefully I transferred over. We'll find out, and if not, we'll have a breakout session to where I can kind of show how that works. All right, so I'm going to start off with a forensically sound demo, which kind of just walks through how PowerForensics parses things. Let me figure out. All right, so for those of you that aren't familiar, we'll do a quick kind of NTFS overview and talk about how PowerForensics actually deals with NTFS. All the buttons are in German, so yeah. Okay, so first thing that we're going to do, the master boot record is the very first thing on a hard drive. There's other partitioning schemes, such as the GUID partition table. In this case, hopefully, it is a master boot record disk, which is going to be interesting. But the idea is that the master boot record kind of gives you information about how the partitions are set up. And so the first thing that we're going to do is we're going to create a hash table for the properties. This is just for prettiness sake and being able to have everything. Ultimately what's happening is I'm going to splat this properties hash list here with invoke forensic DD. So each one of these items, so here in file equals physical drive 0, that is going to be an argument that's passed to invoke forensic DD. I'm just doing it for prettiness sake. And so what we're doing here is we're taking physical drive 0, which is the first physical drive on the system, and then we're going to read from offset 0 to offset 512, and we're going to get a count of 1. So we're going to read 512 bytes, the first ones, and we're going to format it out into hex. Got to run as that might be. Okay, good. All right, so yeah, because we're reading directly from the drive, we need admin in order to do that. So that's the caveat. All right, let's try that again. All right, so, and this is a GUID partition table, so just kind of bear with me while I explain this. And so, in general, what you would see here is a bunch of boot code. So the master boot record has tons of boot code that is just like the first code that runs when you start up your system, and it's going to basically point to this area down here, which is the partition table. And the partition table is going to have up to 4 standard partitions. So it's going to tell you things like the partition is NTFS, the partition starts at offset such and such and goes to offset such and such. And so in this case, it's a GUID partition table, so this is what they call a protective master boot record, which points to the GUID partition table, and then you would parse that. So we're just going to kind of skip over a couple things. Just assume that what I would have showed you here worked, and kind of list out the partition table, and you can use that information. All right. So what we can do, kind of switching up, I'm just going to type it in since this is different. All right. So first thing we're going to do is we're going to do invoke forensic. Ooh. All right. Yep. So I've been working in England, and the backslash in England is in a completely different place than the US, and that's really thrown me off. And I don't know where the backslash is here.
By the funny-looking bee thing.
How do I get to that function?
Alt-GR, it's in the lower right by the spacebar, and then S-set, or the bee-looking thing, is for the backslash.
You know what, we're just going to... Yeah, so, okay, so Alt and what? I see where it is here.
Yeah, so Alt-GR, it's the one on the right. They're different. Yeah, there you go.
There we go. Gotcha. Okay. Hopefully we won't have to type that in here. Okay, so what we're going to do is read from // C:, which is the C logical partition, and then we're going to read from offset 0 to all right, block size 512 bytes, and the count is 1. Then we're going to Alt-GR again into format X. Okay. So what we're going to do is from the logical partition, we kind of skipped how we got here because the master boot record should point us to the actual NTFS bootable partition. And so we're just kind of taking that out of the picture because it's a GPT and I wasn't prepared to work on that yet. We're just going directly to the volume, reading the first 512 bytes of that volume. Count is 1, and it's going to output the volume boot record in hex, right? And so the reason why we know that this is an NTFS formatted partition is we see the header here, NTFS. If you've ever like booted up a bad partition, you'll see an error that says a disk read error occurred, so on and so forth. But in general, this doesn't mean a lot to us, right? Generally, if you're not spending a lot of time reading, hex, then you're not going to know what's going on here, and specifically the volume boot record. So what we can do next is go back. So, we just read raw bytes from the system. What we're going to do now is use Get-Forensic volume boot record to read the actual volume boot record. And now we've interpreted those bytes that we just read, right? And so now we actually understand, for instance, this volume has, a lot of total sectors, whatever that means. And we're able to say that each sector is 512 bytes. We then know that every cluster, is 4096 bytes. We know that an MFT file record is 1024 bytes. And then we know where the actual MFT starts. And so this is starting to kind of build our understanding of how the disk works. So now I'm just going to store that to a variable to reuse going forward. And now we're going to kind of transition onto the master file table, which is a metadata structure which contains information about every file on the partition. Again, I'm going to use, let me make sure that's going to work. Okay, I'm going to use this hash table. So we're using invoke forensic DD again. In file is C colon, out file or offset is going to be derived from the volume boot record. And then the block size is going to also be derived from the volume boot record. So earlier I just pointed out that it was 1024 bytes. And then we're just going to run that. And we're going to, the idea here is to get the first record in the master file table. Now what we see is, this is good to see. We see the file 0 header. We see the file 0 header, and then we see $MFT. And so what $MFT is the master file table keeps a record for itself. The very first record in the master file table is for the master file table itself. It's self-referencing. These things, if you look at hex code, these are going to be timestamps, like Windows file time timestamps. And so, generally we start to understand what's going on. We could read some strings, but again, not a lot of human readable information. So again, we have a commandlet, get forensic file record, which is going to just let us read that information. And so now we see, that's funny, so yeah, the dates are formatted differently than I'm used to seeing them, but yeah, good that it works. Yeah, and so here we see full name, $MFT. We see that it has a parent record number of 5. We see some timestamps associated with it, right? And this is just a single MFT record that we're parsing directly off the disk. All right, so again, we're going to store that in a variable. And then I just kind of want to show, so I just output a variable or an object, right? So this is a true, .NET object. And so we can come back here, and if we want to, for instance, see the properties that are available, then I ran get member, or I took that record object, piped it into get member, looked at the properties, and did format table. It has things like the access time, whether or not the file is deleted, whether it's a directory and not a data file, the born time from the file name attribute. There's also this, where is it? The attribute property, which didn't show by default, but what it is an array of attribute objects, and we'll show that here. And so what we can do is just simply $record.attribute, and it's going to list out a bunch of different attributes about that file. So every MFT record has a number of different attributes that are associated with it. And these contain things like the timestamps, right? And so when you're looking in Windows Explorer, and you see that a file was last modified at time X, that time is being derived from the MFT. Ooh, touchscreen. Yeah. And so this is nothing like testing on a non-English system for the very first time for an applied audience. So these timestamps are being derived. There's also things like the file name is stored in this record. Here, this data attribute is particularly interesting. So for a data file, meaning a actual file and not a directory, we have what they call the data attribute. The data attribute contains information or pointers to where the actual data for that file is stored on disk. And so in this case, we have a file. The MFT itself is this big in bytes, whatever that number is. And then we have these data run objects represent the pointers to where that data is actually stored. Because in this case, it's a fragmented file. That's because in TFS, the master file table grows as you add more files to it. At some point, they couldn't contiguously store all the data, and so they broke it up into two chunks. And so we can then derive where those two chunks are and read the master file table. All right, so now we're going to kind of look at that data attribute again, and that's what it looks like. I just showed that. Now we're going to store it in a variable. And what we're going to do is we're going to use invoke forensic DD to basically read that data, the data runs, and actually make a copy of the MFT somewhere else. So let's just make sure that's... Oh. Okay, so right now what's happening is it's parsing the master file table, determining, and then making a copy using DD of the master file table itself. The reason why we're doing this is because the master file table is a system file, and that file can't actually be accessed directly because it's hidden or locked and all kinds of different things. So let's just, you see this MFT file being written, and as it just keeps getting written. So that's going to take a second. Just showing that, you know, I didn't want to output the entire master file table to screen, so that would take eons. Also, this is a much bigger MFT than I have on my demo. Alright, for time's sake, I'm just going to stop that. But in general, what we did is we started reading in the master file table. Alright, so I'll skip that part. Okay, so then we have this record, and it also has methods, so just kind of a cool deal. If I get my prompts back. Sorry about this. Alright, let's get back to where we were. Alright, so then, we're going to reference that record, and we're going to show the methods that are associated with it. So, in general, what I wanted to show is that we have like a copy file method, so you would be able to just copy a file similar to like copy item. We also have a get content method, which would, instead of doing that for each loop and iterating through the data runs, we'd be able to literally just use get content, and it has the logic to do that for us. So it kind of simplifies things a bit. Let's see. And then kind of the cool thing, so this was just going to show that we're actually copying the real MFT, but we lost time, so I'm just trying to skip through it. What we can do is then we can point get forensic file record at just the C volume, and that's going to parse the entire master file table for us. And we're going to store it into an MFT variable. So it's parsing now, and it just finished. So in that time, we parsed 380,000 MFT records. So now we can reference them if I know where the for arrays. Like
Okay, 8 and 9. So Alt-GR 8 and Alt-GR 9. Alt-GR.
Okay.
Yeah.
So, all right. So now I can reference by the MFT records index and kind of figure out where it is or get its record. So like what's 192? I don't know what that is off the top of my head. Apparently it's in C, Windows old program files, Windows apps, whatever it is, right? And so now we have the entire MFT stored in a variable, and we can go and look at different records based on that information. All right. And then a cool one, so the root directory is always stored as MFT record number 5. And so in this case, if we look at MFT record number 5, we see that it's C:, or it's really actually named period, which represents the root directory. And so we can start kind of working from there. All right, so the MFT doesn't only store data files, it also stores directories, right? Directories are just files, it's just a different kind of file. And so what we can do, I just showed that, but we can store that root directory into a variable. And so now $root represents that record that I just displayed on screen. And they have what they call index root and index allocation attributes, which instead of data, they contain basically information about the files that are contained within that directory. And so we can basically run it against looking for the attribute named index allocation. And here we have an index allocation attribute that has a pointer to where those data runs are. All right, I'm just going to store that in a variable. And index allocation attribute has like a get content. It's actually get bytes method, which allows us to just read the contents of the index allocation attribute. And so I'm going to read that out into hex. And here, what we would be able to see are things like the recovery directory. Oops. I keep clicking and it sends me down to the bottom. So like test WS, If we go up higher, we see like a reference of program files x86, so on and so forth. So these are all the files or directories that are contained within the root directory. So now we're starting to, we went from the master boot record, which gives us the partition table, then went to the volume boot record, which tells us kind of the geometry of how the disk is set up. So what are the sectors, what's the sector size, the cluster size, where's the master file table. Now we've actually looked at the first record or the root directory in the master file table and are trying to understand what files belong in there, right? And so we're starting to figure out our way around that directory or the directory structure. All right. Okay, so now we're going to So there is a, I don't know if it's a bug with my code or with the ISE, but some of the things in PowerForensics don't specifically work in the ISE, so I'm going to use the console. I gotta figure out what this is. Alright, so Jeffrey Snover wrote the start demo script, which just kind of allows me to not have to type it, which is good in this case. Alright, so what we're going to do now is get forensic child item, which works exactly how you think it does, exactly what you think it does, except it's doing it by parsing the MFT, right? So we're going to list the directory contents of the C directory. And so in this case, what we're getting is we have things like the $bad cluster file, or the $volume file, $MFT, but we also have files like program files that you would expect to see, program data. So this is showing literally every file that's referenced by the root directory's index allocation attribute. It also is giving us things like record numbers, right? So these are the offsets or the record number for the MFT for this file. And so for instance, if we were to look at, if we stored, going back here, 37, so it would be $MFT, 37. Sorry, this is kind of close. And there's language back. So just so we're kind of validating the fact that that information is what we expect it to be. All right. So this is just kind of showing, hey, like, you know, we're doing all this parsing, and I just talked about NTFS and made people sleepy. But the reason why that's important is now we actually have the ability to do things and start understanding the layout of how files are stored on the disk. All right, so now, for instance, the $attrdefs file, what it does is it actually describes those attributes for us, those MFT attributes. And so what we're doing is we have basically a reverse lookup commandlet, which allows us to get forensic file record index, allows us to get the MFT index for a specific file path. And so now we know the attrdef file is at MFT index 4. And now we can specifically read the contents of the attrdef file. And so, you know, generally there's some you know, human readable strings, Unicode strings, standard information, attribute list, file name, data, so on and so forth. But like, you know, what is this stuff in between, right? Nobody specifically knows that off the top of their head. And so again, we have a situation to where we found the contents of a file, but we need to be able to actually understand it. So for instance, we have Get-ForensicArtifact volume name C. And now we know that information told us the type number and then the minimum size and the maximum size of that specific attribute. And so this is just kind of displaying the idea that we're parsing all of that information, finding where an actual file exists, and then we're interpreting what the contents of that file means. Because the majority of like really cool forensic files are going to be binary files, and you have to interpret those binary bytes into something that a human can understand. Another pretty cool thing is we can specifically find the SAM, like the index of the SAM file. The SAM file is the registry hive, the security, I forget what the rest of SAM stands for, but it's basically the registry hive that contains all your user information, like password hashes and things of that nature, group membership, local users, things of that nature. All right, so yeah, and then like, what am I doing? Oh, so in this case, what I was showing is that you can like use get child item, the normal PowerShell get child item, pipe that into get forensic file record, and you'll get the forensic file record for every single file in here. So this is going to take a little bit longer because there's more files in the root directory than I'm used to. What you will notice is that getChild item doesn't tell you about those files that are prefixed with a $sign, so like the $MFT, for example. And so we didn't just parse that. And so that's why the Get-ForensicChild item is kind of important from a forensics perspective, because that's going to show you every file, not just the files that the API wants to show you. Okay. All right, so this is, the idea here is that we're using that directory parsing, or that directory parsing in the MFT that I showed you, to determine where the SAM file is on disk, the SAM hive file. And so just using measure command to show how long that should take. So in this case, it took 4 seconds to find that specific MFT record and store it in $R0. And then in this case, we're basically doing piping into where each, and then we're going to look for the SAM. So we're parsing the entire file system. So by actually parsing the MFT and understanding its structure, we were able to actually save ourselves 2.25 seconds or so. So just rather than using like the pipeline, for example. Okay, so this is where it kind of starts to get sexy, I think. In case maybe you thought it was sexy from that. All right, so what we're doing is getting the contents of the SAM hive. So this is just going to read the SAM hive and give us the raw contents of it, which this is using the PowerShell built-in. Oh man, so I guess because the SAM is being used by another process, we can't access it, right? Well, oh no, this is using PowerShell's get content, right? And so PowerShell's get content respects the fact that another process is using that file, and it can't get a handle because the handle's being used by somebody else. Well, what I'm doing is I'm literally finding where the bytes for the SAM hive exist, and then I'm reading those, right? So I'm not technically touching the SAM hive, I'm just touching the bytes that happen to be associated with the SAM hive. And so, give it a second. And there's the bytes that are associated with the SAM hive. Again, none of that means anything to any of us, right? We get to sit here and watch it scroll. But ultimately, we were just able to access the file that we weren't technically supposed to access. And there's a lot of blank space at the bottom of the SAM hive, so that's what's happening here. Okay. So then what we can do is we can try to copy the SAM hive, and again, using copy items, I can tell you, hey, no way, Jose, I can't do that. But we have copy forensic file. The reason why I named it forensic file instead of forensic item is because it literally only works for files, not for like all the other things that get copy item work for. And so we can copy the SAM hive into C demo. So that doesn't exist. So the reason why that didn't work is because the C demo directory doesn't exist, and I can't do that using this. So I'll show that in a second. All right, so then we could use getChild item for the SAM, and I would be showing you how that the SAM size is the same, but apparently we can't do that. All right, so going forward, what I'm doing here is I'm going to start parsing out the registry. And so we're parsing the software hive in this case. Yeah, so another error, demo fail. I promise this all works in real life. So this will work. While that's running, give me a sec. I'm going to start copying some files. Literally nothing is working. So yeah, originally I was going to demo like an investigation against a drive image. That drive image is 26 gigs, and I wasn't able to transfer that over to the computer that I'm using. And so what I have are some recordings from a previous talk that we're just going to investigate. And so kind of the cool thing about how this ties in is that the attack was done with PowerShell Empire, which we'll be talking about in literally next session. And so this is showing kind of the forensic investigation of PowerShell Empire. So it might actually be more, I guess, more related. So kind of the content here is that, or the context, you had like a network-based monitoring, alert, and somebody said, hey, there's a lot of data that was being exfiltrated from the network from XIP, and so can you, go investigate that system and see what happened? And so what we're doing here is they gave us a time frame that occurred, and so we're using getDate to establish a date or a start time. And so I've now since learned that there's a much easier way to do this, but I decided that I wanted to type out year, month, day like this. So just bear with me for a second. I'm going to kind of speed it up. So then you do an end date there, just kind of showing those are the dates there. All right. Physical drive 4 represents I was using F-Response, which is a commercial tool to mount a remote disk image. That represents the C drive on a remote system. What I did is I just parsed out the entire master file table, and now what I'm doing is I'm going to create a window. So using those start and end dates, I'm going to basically say, hey, show me any file that was created within, between the start and end times. All right, so we're running short on time, so I'm just going to that's what we want to show. So we just went from 193,000 files to 15 files that were created within our target time frame. So now what I can do is I can sort that based on born time and start looking through. First thing that jumps out at me is an @ job was created. So I immediately exit out of there. And then I'm going to do get scheduled job raw, which was the old name for my scheduled job parser, which does a better job than the built-in PowerShell one in my opinion. And so now we're seeing that launcher.bat was executed at 2:31 p.m. UTC. So now we know that, what is launcher.bat? That's kind of interesting, right? So let's go and investigate whether or not we can find launcher.bat, which the answer is no. Launcher.bat was deleted. So then there's this thing called the USN journal in NTFS, which is the transaction log. That's going to basically, every time you alter a file, whether it's creation, deletion, adding more data to it, it's getting a record written in the USN journal, which is used typically for like backup software to know what has changed since the last time that I backed up, or it can be used by antivirus to determine what files have been created since the last time that I ran an antivirus scan. That way I don't have to rescan every file. All right, so we're doing a similar process here with the USN journal. We went from nearly 500,000 records to 171 records. Just kind of speeding through because I'm basically out of time. Here we see net1.exe was run using the prefetch. Prefetch gives you an idea of what programs were executed at what time. And that was run around 6:30. And so remember we saw 2:31. 6:30 is the UTC, 2:31 is apparently the local time. And so we see net.exe was run right before which was run at 6:30:31. And we see that a file was created, that job. All right, then we see, like the prefetch for @.exe. Then we see that was overwritten at 6:31, which corresponds with the time that job was scheduled to run. We also see that launcher.bat was deleted, so now we have evidence that that file was deleted at that time. So I'm going to skip forward a little bit further. Just point out some other things. There's some weird WMI stuff and PowerShell stuff, which is inherent to how Empire was working at the time. You see that some stuff was written to the PowerShell event log. Then you see this file called create, or exfil was created, right? So you see the name down there, exfil. You don't know whether that's a directory or a data file, but it was created at 6:34. And then, as we kind of keep scrolling through, You see hamburgerrecipes.txt was created at 6:35, and what that's showing is that that file's parent is that exfil file. So now we kind of have an idea that the exfil file was a directory. We also see finances.csv and passwords.txt are all being added to that exfil file. Then we see exfil.zip was created. All right, and then exfil.zip gets deleted. So now I just want to show, I have one more demo that I want to show. Sorry, we're a little front. Oh, not the attack. I'll let him kind of talk about that. All right, so now what we're going to do is show the file recovery. So we want to get that exfil zip, right? So now we're basically showing we're able to pull the MFT record for exfil zip, and we see that it is marked as deleted. So just a little bit of explanation. When you delete a file on NTFS, it doesn't truly delete the file. What it does is it marks the MFT record as being deleted, meaning that the operating system can reuse that MFT record later on, and that file will remain in existence or on the system until that MFT record gets overwritten. So in this case, we were able to get there in enough time to recover this file. All right, so this is showing the really long way, and I'll skip forward to the cool part. So remember those data attributes. This is telling us the contents of exfil.zip are at start cluster 32148, and they're one cluster in length. So now we know where that is. We use the volume boot record to determine how big a cluster is, in this case 4096 bytes. And then we can use invoke forensic DD, it used to be called invoke DD, to read that file. Now we're just going into evidence. There's exfil.zip. We can open it up, the exfil directory, and all those files that were in it are recovered. All right, so just kind of showing, this is the funny part, I guess. So, what is in the hamburger recipe? Obviously, we're, some sort of burger chain. There's the actual secret hamburger recipe for Krabby Patties from SpongeBob. Mr. Krab got hacked. So that's what happened. So we're able to, at the end of the day, we can tell the customer, hey, somebody attacked you at 6:30 p.m. UTC. The attack lasted roughly, I think it was like 18 minutes or so. They exfilled 3 files that they zipped up into a file called exfil.zip. The 3 files were your finance CSV, and we can go figure out what was in that. Hamburger recipe, your secret, company recipe, and they stole your passwords. And so at the end of the day, we're giving the customer not only that they were attacked, but what data was stolen from them, so they can kind of make their next move based on that. All right, so that's pretty much the end. The last thing that I want to talk about is the future, what I want to do going forward. I'm talking about multiple file system support. So right now I support NTFS because that's common on Windows, but we really want to focus on going forward and working with extended file system, hierarchical file system, which is the Mac file system, FAT, all those types of file systems. SQLite databases, being able to parse those, parsing the ESE database, which is the Windows proprietary database format, and then remoting capabilities. We also have WinPE, which is the pre-installation environment for Windows. We've actually made a bootable thumb drive, which will boot up with a WinPE image that has PowerForensics loaded on it, so you could really just go into, go to a computer, plug in that drive, and you're running PowerForensics on a 1 GB thumb drive, so that's pretty cool. Beyond that, if anybody has any questions, I think Will's talk is supposed to start in 15 minutes, right? 20 minutes. So yeah, we have 20 minutes for any questions. And I apologize about the demo fails that I had.
So I have one question.
Sure.
Do we have a mic or
Yeah.
Okay.
Oh, it's on the table.
When you say with NTFS, there is always danger of overwriting the record.
Yes.
So would be a good idea to install the module on every client, for example?
Yeah, so the question was, if you're trying to be kind of forensically sound and you don't want to overwrite any forensic artifacts, is it a good idea to deploy PowerForensics out to every system in the environment? And my answer is probably not. So you don't want to do just in time and deploy it out when you're doing the investigation. And that was actually something I'm going to show. So thank you for reminding me. One of the cool things that we've been working on, and hopefully it got transferred over here. Okay, yeah, is Get-Forensic File Record portable. So we made PowerForensics portable. And this is pretty cool, kind of like learning from the offensive brethren. What we're doing here is this like super long string which goes on literally for a really long time. We're talking like 80,000 characters. That is the DLL represented in base 64, compressed base 64. So yeah, some people are starting to understand where I'm going with that. And so what we do is we load that into a variable, and then this code here is basically loading that assembly in memory, right? And so we're not ever touching disk. And so PowerForensics, one of the cool things about it is because it's using classes and things of that nature, there's like a public API for everything. And so just like you would do in PowerShell, you call, this is the class PowerForensics.ntfs.fileRecord, which has a get method. And if you pass it a volume name, an index, and then in this case false, there's something about how it parses, but basically you need a volume name and an index, and it's going to give you the output. And so the idea here would be to create one of these little wrappers for every single commandlet, and then you would be able to run it over input command or something along those lines. So I've been working on it. It takes a really long time to replace like 40 commandlets in this manner, and so I just haven't got around to everything, but it's pretty nifty. I guess I could run this real quick. So good. Alright, so then we can do C1, and then we can do index 0. I think this might be an old version of PowerForensics, so let's see here. Let's see what happens when we do that. Alright. Well, yeah, so I just loaded it up, but we can do, so let me check. Led me into another demo file. Yes, it should take a. That's weird. Alright, so what we're going to do is give it a path. Always bring your own keyboard. Yeah. I'm not running as that.
Access denied.
I don't have access. Volume is not ETFs. Okay, apparently. No, so I'm trying to do it from C, but let's see. D is definitely, I don't think D is ETFs format. Oh my goodness. Okay, well, sorry, that's not going to work. But in general, that's the idea. Look, now it's mad at me. The idea would be to take the most current version of PowerForensics, base 64 encode it, and then basically load it into memory. So we were working on like a, Unix has, oh man, what is it called? Network block device is a protocol that Unix uses to basically allow you to connect to a block device like a hard drive over the network. And it's actually relatively simple. Literally, there's a server that is waiting for a request. When it receives a request, the request says, I want to read from this device, so like /dev/SDA or something like that. And then I want to have you start reading from byte 0 to byte X or whatever. And then it will just send those bytes over to you over the network block device protocol. So we were trying to implement a PowerShell version of that, but then you have like authentication and all kinds of things that we didn't want to mess with. So this is in my opinion, the best method to do it. So, are there any other questions? Okay. Yeah, and oh, cool.
Did you think about just doing a function that's the basic component code for you?
So I heard did you think about doing a function?
Yeah, doing something that does this automatically instead of you going through all your methods and doing it by the basic component
So the question is, like the base64 encoding, did you think about making a function? So we have a function, it's in PowerSploit, which is an open source PowerShell module. It's an attack module, but not everything has to be labeled attack or defense. And so you can use that to create this base64 encoded DLL, I guess. So that's the. Anybody else? Okay, well, thank you guys, and again, I'm sorry that